All right, well, as many of you know, I've been in this project for a long time, way longer than I expected. We all have a dream, right? We all have a dream of a 1-meter telescope. So I was the one foolish enough to chase that dream into the physical reality of trying to own one, and this is the exploits. Now, this is more of a laundry list of obstacles that had to be overcome to build this thing than it is, like a fun story. I think I want to point out there's one picture in here where I'm actually smiling. The rest are like, right? So updates are still happening here, but we're restarting now. Let's hope we're getting near the end.
There's progress.
Yeah. So it has been an interesting journey. It has been twists and turns. It has been things that I never expected happen. And that's some of what I'm pointing out to you tonight. So probably by the end of this talk, either you're going to see, now I know how it's done, I think I'm going to try and do it, but I hope you do it before you die, because if you start now, for many of us, you probably won't make it. Or you'll say, boy, am I glad I never even attempted a 1-meter telescope. So as many as you know, in 2000, I detected an exoplanet. This was a known exoplanet. I measured it by radial velocity. And at that time, I had a spectrograph hooked to a 16-inch telescope. And is Sky and Tel here right now? They were here earlier. I don't know if we're here right now. So I went to Sky and Tel. Updates are still underway. We may have to just go here. I went to Sky and Tel. I said, would you be interested in doing an article about this? And they said, no, we just did an article on spectroscopy. Why would we do something like that? I go, well, this is like amateurs doing radial velocity. It's not something that happens every day. So they blew me off. So that kind of pissed me off. And I said, all right, what can I do then to actually get in Sky and Tel? Because back then, that was kind of a big deal, right? And I said, well, can an amateur discover an exoplanet? That was the big question. So can an amateur discover an exoplanet? That was the question. No one had done anything at this point. Remember, this is like in 2000 when Dave Charbonneau, I think, had just discovered the first transiting exoplanet. Everything was done by radial velocity. There was like 60 planets known at the time. And when I started this project, they said, well, how soon will you discover your first exoplanet, right? I said, well, I want to be in under the first 100. Okay.
Oh, wow.
So I think I blew that by quite a margin. It's not even possibility today, right? So if you were going to do discovery of exoplanets, at the time, a 1-meter telescope was the smallest one that was actually discovering them. So you need a big, big scope. And to do a big scope, obviously, you need a big mirror. Now, I'm on a big budget through this whole thing. And one of the reasons why it took a long time is because I own my own business, and small businesses go through ups and downs. I've been through multiple ones. And every time something caved in the business, then a lot of the work would have to stop on the telescope. So that added a lot to it. But it's still, even without all that, it still took a long time. So I started looking through eBay, and miraculously, within a week, this comes up. So this is a big blank. I'll tell you more about it later. But this is where it started. It started in a rotting wooden box in a backyard. And then to give you a preview of where it ends, this is where it ends with a 1.1 meter telescope in my dome. Now, if I just quit here, it would all look fine and dandy, but there's a lot in between those two slides, right? So I'll tell you a little bit about the telescope. It's a Dahl-Kirkham. Primary is F2. Keep that in mind, F2. I have zero experience making a mirror. Zero. All right, let's jump right in. The final is F8. The design was by Eric Palmer, who's a friend of Mark Trueblood's. He worked for Raytheon, and he did infrared spy telescopes from space. He did Hubble look-alike stuff. So it was in pretty good hands there. So this is the mirror in the backyard. Well, it's a blank at this point. So this has a bit of an interesting history. This guy, Norm Oberle, owned this blank. And he actually got two blanks. One of them was a 24-inch. He made that one into a mirror. He was a famous mirror maker from the Cleveland area. He made the 24 into a mirror, and this one was waiting to be his retirement project. The 24 ended up in the Cleveland Astronomical Society's telescope and is being used to this day. Well, before he could get around to this telescope, he died, unfortunately, of cancer. So this was actually sitting in his backyard for a long time, I think somewhere between 5 and 10 years before I came along. And a lot of people knew it was here, and they came to look at it because they wanted to buy it, because 1 meter mirrors are very rare. But there was a problem. There were bubbles in the mirror. Now, as the story goes, this is a quartz blank, which is very, very desirable, right? It's the next thing down from zero Dur in terms of thermal expansion and all that. And the story is this comes from Kitt Peak, and Kitt Peak supposedly made like a dozen of these things, but only needed 6. And these bubbles are a characteristic of when you pour quartz. I guess it happens all the time. This is what I understand. So what they did is they made all of these, and they polished the top and bottom surface of them to see where the bubbles were, and they rejected a bunch of them, and this is one of the rejects, right? So I get the rejects to work with. So everybody came along and looked at these bubbles, and there's pretty substantial bubbles in there, and they said, no, I don't want to have a big hole in my mirror. What I did that was different, this is one of the smarter things I did, I brought a laser with me, and I shined it in at a 45-degree angle, and I could see it hit the bubble, and I could tell how far down it was from the surface, and I realized by doing that, I only hit a couple of very small bubbles in the surface, which you may see if you look carefully down the road. So now I've got a blank. It weighs over 900 pounds. All right. There's no lightning here. This thing is 900 pounds of glass. And I heard a lot about, oh, you're never going to cool this thing off, et cetera, et cetera, et cetera. So I was kind of up against it right off the bat. So the next thing I need is a grinding machine. Because for a mirror that weighs 900 pounds, you can't build something out of 2x4s, right? That's just not going to work. You've seen some grinding machines made out of 2x4s. They'll work for 16, not going to work for a thing that weighs half of a car. So again, my friend Mark Trueblood, who was working at NOAO at the time, NOAO was getting rid of their mirror making capability in favor of bigger telescopes. They originally had some smaller ones. And they had a grinding machine in their backyard, in their lot. And Mark finagled something because they're not supposed to let it go out to the public, right? It was supposed to be scrapped for steel and stuff. So Mark talked to some people who talked to some people, and I was able to get the grinding machine. So here it is, putting the blank onto the grinding machine. And the edges of the blank were kind of flat. They put up boards when they cast it, or ceramic plates when they cast it. So the first thing that had to happen, it had to be ground round. Now this is a little bit later picture, but this gives you a better idea of what the grinding machine looked like. And you can see things like this are half-inch steel. These are super bearings. Had a whole gear mechanism under here, lots of controls, lead weights, counterweights for the thing. And here it is. We ground the outside round, and then we started polishing.
Tom, may I ask a question?
Sure.
Who's the young man in the picture?
So this is John. I thought it was John Fritzl worked with me during this time, and if you see something off camera, it's probably him. A lot of people work with me in this whole project, so a lot of times I'm going to say we in this project. So understand that I'm trying never to discount anybody who has a lot of help on this. So we get the mirror, we get it on the grinding machine, and we start working our way into it. Now, at this point, I'm consulting the experts, right? So Dan Joyce of Chicago is a very famous mirror maker guy in Chicago. He's made a bunch of mirrors. I said, Dan, come over here and tell me what to do to start grinding this mirror. He said, okay, make yourself a pitch lap, put ceramic discs on the front. He goes, get the hardest, the toughest grinding grit you can get, Black Beauty, I think it was called, and you start grinding and you work your way into the middle of the blank until you get the curvature you want. Okay, sounds pretty simple. So we get the machine going, we start grinding away on this thing, we start measuring how fast we're going down into the mirror. We have to go 1 3/4 inches into the mirror, all right, for an F2, 1 3/4 inches. At the rate we were going, we estimated it would take 20 years to get there. Didn't know. Okay, so now we're faced with a really big obstacle. How the hell do I even get it close to the shape? I wasn't worried about figure at this point, I just wanted to get it close to the shape. Brute force, baby, brute force. So what you see here is there is a square piece of aluminum that goes up into the ceiling up here. I'll show you another picture in a second, and bolts to a heim joint up there at the radius of curvature. And then we clamped a hand grinder with a diamond wheel on it. Okay. We put an all-thread here, and John hand cranked it into the mirror. Now it didn't just like blast through the mirror. You could only do maybe 1/8 of an inch at a time, but it went a hell of a lot faster than what we were doing before. So he probably spent a couple of weeks grinding on this thing. Here it is actually in action here. We had water going on it, and we went through many diamond wheels getting through this thing. All right. So that's what it took to get in, get it even close. So now that we've got the mirror, it's roughed out, there's another thing you need. You need a way to measure the mirror. That required an interferometer. So did I know how to make an interferometer? No clue. All right, no, not a clue. Never made one before. But Eric Palmer, our genius PhD optician, says, oh yeah, you can make a great interferometer with a little beam splitter cube, a microscope lens, and a helium neon laser. Okay. That's what ended up happening here. I'm going to come back to this in a second, but this is the layout. All right. This is kind of interesting. Kind of keep it in the back of your mind. If you're ever building 1 meter and you need an interferometer, this is a good choice. This is the laser coming into a microscope lens, a microscope objective. You set this thing up so you focus the microscope objective on this pinhole that's glued to the 50-50 beam splitter right here. Once you get it in focus, you put glue all around the outside here to lock it all in position. Then it throws a wave out to here, comes back, interferes with itself along this plane, and if you're looking in this top part of the cube, you can see the fringes. Well, we got an interferometer. Well, that's only part of the interferometer, because you also need corrector lenses, or nulling. These are nulling lenses. Technically, they're nulling lenses, not the correctors like we're used to in adult Kirkham. An interferometer can only see a sphere, and if you get a sphere, you'll get straight lines. If you're actually going for an ellipsoid, which is what we were going for in this design, it's not a parabola, it's a little less material removal for an ellipsoid. In order to get straight lines so you know you're good, you have to have these null lenses in place to deform everything, so when you do get straight lines, you know you've got your ellipsoid in place. Does that make sense? So we're deforming everything so that we can go for straight lines. I had these professionally made because this is where the Hubble went wrong. All right? The Hubble went wrong because they thought they had a problem. They tweaked a null lens, and it said, oh, it's fine now. Let's send it up into space. So it was a nervous thing. Now, the other problem is that we have to control this thing because it had to go up in the ceiling. And when I say up in the ceiling, my ceiling wasn't tall enough for the focus of the mirror. I had to cut a hole in the ceiling and glue a 55-gallon drum on top of the industrial building, right? And then this mount, there's a mount on this thing. I don't know if you can see it. No. We had to do the mount. You can see it sticking out right here and here. It had to be bolted to the I-beam because any vibration in the interferometer will screw up your fringes. It still screwed up the fringes, but it was much less than if it was on the roof. So now we've got an interferometer mounted in the ceiling at the focus, but we're still not there yet because you've got to be able to control this thing mechanically, X, Y, and focus. And you have to be able to see where the return dot is from 20 feet down below. So you see these pulleys? Had ropes going over the pulleys. So you could X, Y it, right? You see this video camera here? It's looking up at the dot, much like the problem you guys have with the spectrograph, where if the spectrograph's not on the hole, you can see where it is. Same strategy here. This is looking up to see where the dot is on the metal plate, and we have to get it through the hole that goes up into the beam splitter. And then there's another video camera on top that we're actually looking at on a TV screen, RF feed, not CCD, anything like that. So there's a focusing motor in back that slides the whole thing up and down. Corrector lenses are mounted down in here. They have to be very precise and on axis, et cetera, et cetera. So now we got that. We tested it on, this is a good mirror, but even if you get fringes, you need to be able to measure them, all right? Because you can't just look at fringes and say you're good to go. You want to have some kind of actual quantitative measurement. So we go to our buddy Doug George, Maxim DL, and most of you don't know, he produced this program called Quick Fringe that will actually, if everything's good, will draw dots on your fringes and then give you an analysis of where you're at and a whole interpretation. So that was kind of the final step to getting everything we need to really get the mirror going. So we started working on it. The first thing you want to do is get it into a sphere. And the sphere wasn't that difficult, but what was trickier is the size of the pitch laps that we were using. They were hundreds of pounds. The biggest one was hundreds of pounds. So we had to put a crane on the side of it. You saw it in the previous picture. I'm holding onto the cable of the crane. And the biggest fear was that if you've seen making mirrors, occasionally if you don't keep it lubricated, the thing will stick on the mirror. If you stick a 100-pound disc like this on the mirror, it does not want to come off. One time it stuck so bad we had to drill down through it and blow air through the center so we could blow it off of the mirror. So after that, it was very careful to keep it saturated with liquid. So we're doing that, and then once you get it into a sphere, you have to take down the outer edge, you leave the 60% zone alone, and you take down the center. So that's how you get to your parabola. So in essence, you're doing this. You want to work the outer edge, you want to work the center. So that was tricky. And doing that led to a lot of interesting things. Here is a disc working the outer edge, and there's almost no way you can't turn the edge. You heard about a lot of mirrors, oh, it's got a turned edge, it's got a turned edge. Well, there's almost no way you can't turn the edge. I mean, if you've got one that's like that, I don't know how he did it. I don't know how he did it. Now, again, I'm talking to people that had done this at this point, and this is what made sense. We also did things like a star lap. We tried different configurations of laps and things like that. I even tried a square one to work down the edge and not screw anything up. But slowly but surely, it made progress. So this is what the progress looked like. This is where we started. Now, this is a Rankiegram here. This is the interferometer. So we also used a Rankine, because a Rankine will give you a much quicker, much easier to deal with visualization of where you are. But it's not anywhere near as accurate as the fringes on an interferometer. So here we've worked the center out, and you see we've got some pretty straight lines. Here we start working the edge, it's looking pretty good. Here we've got the nulls in now. So the nulls are in, and we're getting closer to what we're looking for. We're looking for straight lines across this. So, was the figure easy to deal with? No, it wasn't. Turns out, failed 3 times to get the figure and had to go back to a sphere. And each time was a lot of work, because I'm polishing through 150 waves of glass. So the first time was really stupid, because I left for a summer vacation and the room that the laps were in got hot and the pitch fell off. And when the pitch falls off, you got to go back to the sphere, because you can't just start a new pitch, a new lap, and reform the pitch on your figured mirror. Second time, there was about a 1/16 of an inch height difference as the edge of the mirror went around, and it lifted up about a 1/16 of an inch. But that's not, is that really a big deal? Well, it turns out when you're lifting a 100-pound pitch lap every half rotation, it wears that side more than the other side, and you can't possibly get a circular, correct mirror. You can't do it. Had to go back a third time. So at this point, we're looking at 2007, right? And we're now 7 years into this, and I'm not even halfway done. We moved to Arizona here, or not here, by Mark Trubel's place, southeastern Arizona. My wife left. I had to stay to finish the mirror. So my 100% job when I was still waiting to move myself down to Arizona was get this mirror finished, because I had nowhere in our new place to put something in a hole in the ceiling like this and get it done. So I blitzed this thing out, and you can see this. I started writing down all the time. This is by no means all of them. This goes from about December to about March, and this was just when I was keeping track of everything. But if you look, like right here, it says straight fringes, and this is like 3507, right? And then there's another thing here somewhere that says final polish. Where is that? Yeah.
Right there.
Yeah, final polish. You can see, yeah, right there, final polish, right? So I thought I'm done. And then here, that's 311. Fringes went bad in the middle. Yeah, kind of tough. So at this point, I'm between a rock and a hard place. I was working under the idea that I did not have to be a 10th wave or even a quarter wave. There's an idea, maybe somebody will clear me up if I'm wrong about this, that the bigger the telescope you have, the more seeing you grab, and it's kind of hopeless to make it even more precise than it really needs to be. So I started weighing all this balances. I realized we're not getting into a quarter wave thing here. So when it finally finished, this is what it looked like. Now, if you look at the Rankine looked pretty good, right? The Rankine looked very possible. Looked pretty good. If you look at the fringes, you see, well, okay, there's some stuff going on here. All that. How bad was it? Well, here is a circular interpolation of the whole circle, And if you look in the zone that counts, because my secondary comes out to about here, this is where I screwed up the fringes in the middle, but most of it didn't count. This is about a half a wave. And this is at the CCD. So at the end of the day, got a mirror, half wave, probably good enough. Not 100% sure because I couldn't look through it, right? And I had to quit and go. Now, one more problem. I need a hole in the piece of a 6-inch glass. How do you cut a hole in the middle of this thing and not destroy your 7 years of work in this thing? No diamond saws. I think it's a 10-inch hole. No diamond saws. So I got a stainless steel pot, and I turned it upside down, and I put a bunch of black beauty in there. I just started spinning it, and it spun all the way in. And then I flipped the mirror over, and I had to come in from the other side, because if you try and punch out the other side, it'll take a bunch of glass with it off the ends. So I punched it from the other side, and miraculously they lined up with a little tiny bump in the middle, which I ground out. But yeah, so I cut a hole in the middle of this thing with a stainless steel pot. Lost about half the pot in the process, but it was fine. So now I believe in my heart's heart that I got a mirror, but I don't really have any way to qualify it. So I did this. I took it out outside the shop, and I tilted it up in the box, and I put my DSLR camera on a tripod up here at prime focus. And I did just an exposure to see what would happen. And I got what I'd call something that's not totally out of focus. It's not a blob, right? So I had a reasonable idea that my star would at least be this big no matter how bad it was. So I thought, okay, all right, we could probably live with that. I'll risk it, and I'll go to Arizona. So I make the move to Arizona, and now we need still the corrector lenses, and we need the secondary. All right, so after all this time, I wasn't fooling around anymore. I had them made. I just had them made at Torque here in Tucson. And they did a great job on it. And I'm smiling. This is the picture where I'm smiling. This is one of the happier days. I thought, okay, I'm close now. Not really. Then again, I'm desperate to know if this thing is doing a good image. So I took a huge risk. I chandeliered the pieces over my valuable primary. I snuck in between the pallets down there and tried to see something with an eyepiece. And there was no hope. There was no hope. So I abandoned that idea. Fortunately, I did not smash anything into my mirror. Another problem was, speaking of smashing things in the mirror, when you have an interferometer up over your mirror, you don't want to drop a tool or anything, or you don't want a piece of the interferometer to come off and drop 16 feet on your mirror. So that was always a concern. Fortunately, it did not happen. So if you're going to have a big telescope, the next thing you need is a dome. So now I was in Arizona. I'm in a good place. My backyard, I've got plenty of room for a dome. I needed an 18-foot dome. 16-foot would not fit this behemoth. It was an alt-az, so it's a little shorter than it would be if it was on a fork. And the price of an 18-foot dome is not double, but it's at least 50 or 60% more than a 16-foot. I'm just telling you this, just stick this in the back of your head. And I called them and I said, why is the 18 so expensive? They said, because we use the hardware from our 30 and 40-foot domes starting on the 18-foot. So the 18-foot has all different hardware, bearings, rollers, all that stuff. He said, literally, the 16-foot dome has got garage rollers and stuff like that in it. He said, so you've got the best stuff you're paying for. So now we're in 2000. This is the configuration. This is not the final design, but it's getting closer here. This is the cage, I call it. You'll see that in a bit. And the dome is going to be sitting up about 10 feet above the ground, so as the telescope get away from the ground scene. So this construction started in 2009. It took a while to finish. This was another very stupid move. Do not assemble a dome on top of the structure you're going to leave it on. This was ridiculous. We had a big scaffolding going up through the middle, but these pieces slide in from the top. So you're hanging this big 8-9 foot piece out into the wind, 20 feet in the air, trying to slide it into the one next to it. And I found out I could rent a crane. They would come out for $300 and lift it up and stick it on my support beams. All right. It would have been a ton easier and less dangerous if I did it from the ground. So don't make that mistake. Here's what it looks like once it was finished. So it was great. And it took me so long to get the telescope together that this siding here actually got torn off by the wind and had to all be replaced before I got the telescope done. So while I had this was constructed and I was still working on the big telescope, I did have small telescopes in here doing exoplanet searches and stuff like that. So I got the dome. Now we got to think about actually the telescope itself. And back in 2003, I knew I had a big heavy mirror here. So I knew if I tried to put it on some kind of fork mount, it was going to be a big flex thing. The fork would have to be hugely substantial not to make a mess of everything. So I was trying to conceive of designs that would put the center of gravity in the middle, and if you twisted the thing around, it wouldn't flex anything. This was one of the interesting ideas. This would theoretically be a bowling ball. It would go into a cup here that you either have air or oil that the thing would float on. And then your fork could be very lightweight because it's just steering the stuff around. It's not actually supporting any weight. So that was an early design. Then I kind of settled on the alt-as design. Here's an early design there. And then this is the final design done in SolidWorks. You can see this is the drive ring for the alt. It had like 8 fans designed into the edges here because everyone said that the mirror is going to have a temperature problem. So now, how do you build this telescope, this monster thing? And I didn't have finite element analysis or anything, and I knew that flexing would be a problem with this much weight, so I just went overkill. I did everything out of 1/4-inch steel. Everything out of 1/4-inch steel. And I used the steel that had the least tendency to thermally expand and contract, and when you weld it, when you weld a weldment together like this and it heats up and cools off, it'll also do a bunch of torquing. And I solved that problem a different way, but I'll show you. So I went to another friend of mine, because I've been in the manufacturing business a long time. He had $1 million laser that he could cut 1/4-inch steel out to within a few thousandths accuracy. So he cut out all the pieces for me, like in one day. I went to Chicago to do it. He cut it all out. It's a 9-point mount, because it's like a 6-to-1 ratio on this blank, so I didn't need much of a support. A 9-point support's fine. And this is how it goes together. So the plate you just saw goes on top of here, and everything was pinned through holes to hold it in place. So you see all these little holes drop into these holes, and then everything gets welded. Here it is, test fitting it. And you see the side plates, there's the fan hole in there. So it's got a big, chunky piece of steel. So I got it all back to my shop. This is inside of my shop, and it's on my welding table, and I started welding it together. You can see how it's coming together now, and you get an idea. This is the center hub that everything mounts to. This is a parallel ground, both sides, so everything remains optically on center. This is the spider. This worked out great. This was very simple, just laser cut rings and aluminum 1/2-inch rod standoffs bolted together. Wonderful. Steel veins. That's been one of the least problematic things. But another thing you need is these corrector lenses. So the corrector lenses have to go into these holders because they have to be very precisely spaced. So you need to piston them to each other and then to the primary and the secondary. So with this design, there was very little flexibility in what you focus. So I don't even focus the secondary. All the focusing happens in the back. And this is the correctors mounted on the central baffle tube. Now the central baffle tube is 3/8 steel. So again, not fooling around. Not fooling around. You'll see why in a second, because I end up supporting the weight of the mirror on this center tube here. So now I got something that's starting to resemble a telescope. This is what it looks like in pieces here. Here I was trying to focus it on the mountain range far away. Again, no chance. I mean, every time I went to do this thing, it would just defy me. It never wanted to make me happy. So I still didn't know at this point if I had a really great telescope or not. So this thing's not coated. The secondaries are. Corrector lenses are in. You should be able to get a reflection even off of just the clear glass. It reflects 3%. And it should give you an image no matter what. But it turned out collimation's a lot trickier than I had suspected. So now we're going to move on to the mount. So you got to mount this thing, and I had looked at a bunch of mounts, and I decided on alt-as, but I was going to pattern it after the wind telescope on Kitt Peak, because it has this I call it the snow cone design. I doubt they call it that, but all the weight is on a central bearing right here, which I thought was a really great idea. So all the weight's in one place. You then have rollers out at the edge here that do the driving and the alignment, and you just spin this thing around. So this was my idea. This is what I'm calling the cage snow cone bearings. So this is the cage going up in the dome. So this is made from oil field pipe, which you'd think is a joke, but actually it's super high quality steel. You can't cut this stuff with an abrasive saw, right? I had to use a plasma torch to cut this stuff. And you can get it super cheap at the oil fields where I hang out in Wyoming, right? Because they pull these things out and they throw them away, and people use them for fencing and things like that. So this is all oil field pipe. So this is the beginning of it. Here is the box tube. This is the platform that you walk around on the second story. And then this is one of the cuter things about the mount. I'm the only amateur telescope that has a stairway built into the mount. So yeah, you walk up the stairs on the side of the telescope and get up to the level, the platform level. So this is the snow cone design. This is the original concept here. And this is what it looks like in position now. Everything that's orange spins. So everything that's orange spins. The bearing is right down here. There's idler bearings up here that hold into position, and I'll talk about the drive motor in a second here. So this looks fine and dandy here, but this was another big story that it took a long time to resolve. This is the ring, the drive ring, welded onto the orange structure. But notice that there's tabs here. I did not weld it directly to the box tube because this ring has to be really perfectly round. All of your tracking is going to be decided on how round you get this ring. If I screw it up, like so many other things I've screwed up in this thing, I want to be able to cut it off and start again. So I tabbed it into position here. Now, how do you grind it round? Because I had them roll it, and it rolled to within about 1/8 of an inch, maybe 1/4 of an inch round, and I welded it in place as round as I could get it. So I said, okay, I've got to grind it. Right? This is when it came in from the bender, the guy that does the circular bending. Here it is, mounting it with the C-clamps and the tabs. Now, where do I go from here? Well, you got to get it up in position first. Now, it's not round yet, right? It's not round. Welded the pieces in place, and this central tube here goes up further than the ring. It's not like that now. It was cut off, but it was done with that on purpose because that central tube comes up here, and there's a cross brace welded across the cage, and there's a bearing right here, so this thing spins like a top. So this thing is spinning, and it's being guided by this bearing and the one at the bottom. So now I'm free to start grinding this and make it round. Well, another thing I thought wasn't going to be too hard turned out to be a real difficult problem. So the next thing I had to do, I had to spin this thing while I'm grinding it. So this is a drive motor to spin the ring. And the first thing I did, of many things, was I took the grinder out of my shop and I mounted it on a slide, and I started grinding away like you would with a surface grinder. If you've ever seen a surface grinder, they do a beautiful job. Zing, 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 just grinds away the stuff. The thing shaked all over the place. Wouldn't work. Okay, one down. Then I got a hand grinder, and I bought a steel saw. I go, okay, I'm going to chew into the steel now. I'm going to get it done. I'm going to get started. That didn't work. Finally, I got a grinding wheel that worked. Now the problem was, it was so loud in there, if you even took your earmuffs off for a second, your ears would be ringing for a day. Because all the sound is being focused by the dome. The dome is focusing all the thing. And you could, my neighbors, and you can't hardly see my neighbors, right? They could hear it all. And it took me a month of grinding to do this. All right, this is a month of grinding 8 hours a day. So, yeah, it was pretty rough. By the end of it, I couldn't sit there and do this mechanically. So by the end of it, I put a dovetail slide on this thing, a stepper motor, and an Arduino controller, and I steppered it down on this thing. I would go into the house, take my earmuffs off, I'd come back in an hour, and I reset it again and let it go make another pass. You could only take not even a 1/16 of an inch. You know, it was probably 30 or 40 thousandths of an inch at a time. So, okay, So making progress. All right, now we're getting close. And it's getting rounder and everything, right? We're going. So, there was a problem. One spot was low. And based on how much effort I'd done to take it down this far, I knew it was going to be like 2 months. Again, you sound familiar? It was going to be 2 months before I could grind it down to the point at the bottom of this thing. So I had to weld it up. I hand ground it close, and I started the grinding process all over again. So, yeah, this was a real effort. Don't do what I did. So by the end of the day, I did get it round. Even though it looks kind of funny here, it's actually pretty smooth. It's round. The whole thing is round to within 15 thousandths, so plus or minus 7 thousandths. So did I know if that was going to be good enough or not? I'm assuming it's going to be good enough. All right, going to be good enough. Because if you think about it, over a few inches of travel across the sky, there's not much deviation in this thing. You'd have to make a full lap before you really see any kind of deviation. So the drive motors came to me courtesy again of Mark Trueblood, one of my bigger benefactors. These drive motors are AC servo motors, which have been kind of a thing lately. People have been hearing about them. These are actually quite old. How old were they, Mark? How long had you had them? Like 10 years, 15 years?
I had them about 10 years.
Yeah, about 10 years. So they were brand new. He got them as a donation or something that they quit the project on. But these motors are very low RPM. They're only 60 RPM, but they're super high torque. And they were actually originally designed for robotic arms. They wanted to be able to bolt it into a robotic arm and move the arm without having any gearing, which was the original idea behind this thing. So the next problem was I have all this investment in my ring, right? I have months of grinding investment in the ring. I'm going to go metal to metal on the ring to drive it. I don't want to do a steel ring here because if I grind a divot into that damn big ring, I'm going to be out again. So I made it out of aluminum. So that way, if something goes wrong and something skids across, take out the aluminum. I can make another one of those in half an hour. And the whole thing is spring-loaded against the drive wheel. So here is the mechanism. That's the drive rim. This is the spring-loading mechanism. The spring-loading mechanism also has the advantage that if something stops abruptly on the telescope, the spring-loading mechanism gives it a little shock absorption. Because this thing weighs, I don't know how much it weighs, but it's somewhere between 2,000 and 3,000 pounds as you're spinning around up there. If it has to stop abruptly, that's a lot of force. So that finally got taken care of. So the bearings on this thing are carrying a lot of weight. This is one of the bearings, again, donation from Mark. Notice that there's not balls in these things. These are footballs in there, and there's 2 rows of them, right? These are footballs. There's a row here and a row behind it you can't see very well. So the footballs allow this thing to pivot. So it's not a fixed bearing like you normally see. So even if I'm off a little bit, if I'm not precise on the thing, it'll just accommodate it. So I've got one of these bearings at the bottom, and this is the one for the alt axis. And this is the drive side for the alt axis. This is the drive rim. This one was another one that was laser cut, and when you laser cut something, there's a texture on the outside there. And I didn't have a way to grind it perfectly smooth. So I just took a belt sander and I belt sanded the whole edge. Smooth, right? Hasn't been a problem. It has not been a problem. So I'll take it. We'll take it. Again, this is some of the wiring stuff. Wiring is always a big problem. Ask Gary Cole. I use industrial cable routing stuff. I know this from my industrial background, making this kind of stuff for a living. So next question is, how are we going to support the thing? I mentioned it earlier. The whole mirror is supported on this piece right here. So it only needs to be supported on the part where the weight's pushing down. So you can see from the micrometer here, this is about 8-10 inches across, fairly small. There's a rim of urethane on here, so it's not metal against glass. And when it sits in the telescope, you'll see it right here. It supports the weight of the mirror. This is that big 3/8 steel tube that I showed you earlier, holding onto the correctors. And that's how it works. Again, no problems there. So now we got something that looks like a telescope. We got stuff mounted together. And the last problem is, let's coat the mirror. Now, a lot of people have mirror coated. The mirror's been coated, right? We all know you could go somewhere and get your mirror coated. You have to pay some money for it, but you could get it done. Not me. Nope. No one would coat my mirror. All right. The only guy that could do it, that had the capability to do it, is Clausing up in Illinois. I'd had him do stuff for me before, right? And Clausing just screwed up that guy's 50-inch mirror. The guy from Illinois that does, I think he does asteroids or something. He screwed up this guy's 50-inch mirror. I said, okay, this guy's going to be kind of pliable. Maybe I'll get a deal, right? So I called him up and I said, hi. I said, it's Tom Kay. I got this big 1-meter mirror, weighs 900 pounds. He goes, okay. I said, yeah. I said, I heard you had some problems with some telescope mirrors. He blew up at me. So he says, I've been doing this for like 40 years, and I screw up one telescope, and it goes all around, and now everybody's down on me. I said, well, hey, listen, I'm willing to give you a shot. I want you to do this mirror, right? So he goes, okay. So he kind of calmed down a bit. I kind of pushed his button. I didn't mean to, but... So he said, what is the mirror? I said, it's quartz, okay, it's 900 pounds, it's 44 inches, okay. He goes, where'd the mirror come from? And I said, well, it was a reject from Kitt Peak. And he said, why is it a reject? I said, because it had bubbles in it. He said, I'm not going to do the mirror. I go, what do you mean you're not going to do the mirror? He goes, it's got bubbles in it, I'm not going to do the mirror. I go, why? He goes, I'm not going to risk that mirror cracking in the vacuum chamber. Right? So, damn, I was screwed up, right? I did get one quote for $50,000 from a place in California. $50K. I said, why is it so expensive? They said, because we can't handle that weight. We have to build you a fixture to hold this thing. Right, so that was out of the question. Didn't have the money. So, as has happened so many times in this whole project over the 2 decades I've been doing on it, something happens and the clouds appear and some blue sky shines in. And I found this vacuum chamber in Tucson. All right, in Tucson. So this is a vacuum chamber. This is about 5 feet across. This thing's big. It's on railroad rails to move back and forth. The diffusion pumps on this thing are ridiculously huge. Now, and this guy was willing to do it for me super cheap. Bob, he's a great guy. We're great friends now, actually. There's one problem. For this thing to work, you've got to hold the mirror face down in the chamber and spin it. You've got to spin it. He's got no way to do that, all right? Well, at least I was talking to a guy that will talk back to me. So I had to build this thing to hold the mirror, and it's got rollers angled for the inside of his chamber, and this one goes on top, so it ka-chinks once you put the weight of the mirror on it. And then a motor goes on here to spin it. I put Teflon plugs in here because I didn't want to wreck my nice surface on the mirror. So here we are loading it into the chamber. Now again, if we were to drop this thing at this point, it would all be over pretty quick. So we put it in the chamber, and we ran it, and we coated it with aluminum. And after a couple tries, it took more than one try, we got a nice shiny aluminum coat on it. So this is what it looked like when we finally made it happen. So great. So now the thing is coming together. Now it's now 2021. All right, so we're 20 years into this thing now. Here it is getting craned into the dome. The mirror is in it at this point, so I'm craning it in. And here it is in the next year, 2022, with the electronics on board. I'm a big fan of putting all the electronics on the telescope. Fortunately, it's big enough that I can put whatever electronics I want on it. So this is all riding on the telescope. This is, just for FYI, what it's using. It uses a SciTech control. SciTech has got a big AC servo one they use for big telescopes. And I've got one of those. Optech focus rotator. It's the Gemini. Nuke computer, Apogee CCD. Lesve dome controls the dome. ACT, MaxMDL, SkyX, Python. That's kind of standard run-of-the-mill stuff. So here is collimation. So it turns out collimation is a super bitch on this thing. It took quite a bit to do, a lot of back and forth, and finally, it started like this, and it took a week to really get to the point where I knew which way it was going and what it was doing. Finally got a star image. So this was the first time I actually saw an image, and I'm calling first light in 2022 here. This is what it came out like. So in 22 years, I finally found out I actually have a telescope that will actually take a picture. All right, how did I feel? This is how I felt, all right? Great. Finally, I felt wonderful. 2023, this is the instrument carousel on the back. In 2022, I just had cobbled the camera on the back. This is the rotator focuser thing, guide camera, fiber optic feed, apogee CCD, etc., other things. It's got a motorized flip mirror that'll go in and out for the fiber feed or whatever else you want to feed there. So, after telling you all this, right, if you ask the question, is it finished? Houston, we have a problem. Okay? We have a coding problem. This was one of the most disappointing things about this whole deal. I mean, I put up with a lot to get here. But I do a lot of observing with Bruce Gary. And Bruce has got a 16-inch, right? And we observe the same star a lot of times because we're looking for very fine dips and we want to make sure that it's not noise. So if we coordinate on a dip, we know it's real. So this is Bruce Gary's light curve, 16th magnitude white dwarf. And you can see it's about plus or minus 1, right? Here's my light curve on a 44-inch, about the same. How did I feel about this? Ta-da. So, this is where I got my crash course in coatings. When I had the optics made, baby, I thought I'm going to be swimming in photons, right? I'm going to have more photons possibly I'm going to need. When they asked me on the secondary and on the corrector lenses what kind of coatings you want, I said mag fluor. Let's just go mag fluor, easy peasy, right? No problem. Get mag fluoride coating. When he coated the main mirror, it was with aluminum only. He could not do multi-coating on there. So again, I'm going to be swimming in photons, not going to be an issue. Well, now we know that's not the case. So the original coatings were magnesium fluoride. The secondary was magnesium fluoride. The primary is raw aluminum. And I figured out a way, and you should all take note of this. I mean, you can forget about everything else I'm telling you, but you should take note of this. Super easy way to measure the reflectivity of your mirror. Now, and somebody wrote a white paper on this thing. It's pretty accurate. It's accurate to like 1 or 2%, which for our purposes is plenty good enough. So you take a white card. I've got this on a little 3D printed thing here. Put a white card 90 degrees to your mirror. Take your SLR camera. Take a picture of the card and the mirror at 45 degrees, right? And this is the picture you get. You put it in maximum DL and you measure the difference between the two colors, and that percentage is how reflective your mirror is. Right? Like, it's obvious now that I pointed out. Sure, it worked great. So, the mirror was 86% reflective, which is actually normal for raw aluminum. But I'm losing 14% there of the possibility, right? And you guys have these star bright coatings and stuff. They're like 98, 99% reflective. So I was losing 14% there. Okay. Well, how about the corrector lens? So I did something similar with the corrector lenses. They were a 10% loss. So my total loss, and this is based on, this is 14, is not, 10% correctors is here, but it was actually worse than that, but I'll tell you that in a second. So I said, okay, I got a problem. So first thing I did is I sent in the correctors and the secondary to get recoated. And it went to Spectrum down in Florida. They stripped off the original aluminum, and they were able to put on a new coating, a multi-layer. It came out beautiful, less than 1% loss. I told them on the corrector lenses, I couldn't quite tell if there was mag fluor on there or not. It didn't quite have that sheen. I couldn't quite really tell. I said, check it out. If it's got mag fluor, don't do anything. He recoated them with mag fluor again. So now it was 14% loss on the correctors. So the problem was, you can't take this stuff off of a corrector. It cannot be chemically removed. Word to the wise. Don't get magnesium fluoride if you're going to try and take it off. Now, I don't know if there's other ones that can be taken off, but I was really stuck now. I had to take my nice, custom-made, commercially produced, I paid for them, corrector lenses, and create a pitch lap and polish them off, and then have them recoated with a multi-layer titanium silicon coating, and now the losses are less than 1%. So that was solved. That was solved. A little scary. But now I got to coat the primary. Now I'm out of options. My aluminum guy did a great job. I'm not complaining at all, but just aluminum's not up to speed. So I took the mirror out again, took the telescope apart, took the mirror out again. I put it in my barn. I stripped off the aluminum coating with nasty nitric acid. Don't use that without a respirator. This is what it looked like after I took all the hard-won aluminum off of it. And I spray silvered it, like you do for a mirror. Spray silver. Yes, it's a thing. It's a chemical thing. You buy this kit, and they use it mostly for antique mirrors. You can strip the stuff off, spray this thing on the back, and then you get your refinish your antique mirror. Well, they also do it with some telescopes. So you spray on, you keep it wet, so the whole process is wet. It's kind of a miracle. You spray on this stuff, and then you spray on this tin stuff that is the adhesion layer. You don't even see the tin, it's still clear. And then you start spraying on the silver. And the clear glass goes to gray, and then suddenly looks like this. Is it perfect? No. You see some stuff here? That's because now I know how to spray it. I was spraying it from the edge, and if you get any dirt from the edge going in, it causes these problems. But this splotchy area is still highly reflective. It's not like it's not worse than the aluminum. Let's put it that way. Not worse than the aluminum. So once I got to that point, the reflectivity is now 98.5% on the primary. Now, you're all going to say, yeah, but Tom, doesn't silver corrode? Yes, it does. Yes, it does. I didn't have many choices. I had hope, though. I had hope. Again, hope clouds part. NASA supposedly just developed this new coating that goes over the silver and will seal it. And it was very new at the time, but the advanced aging tests looked like it was going to last maybe 6, 7, 8 years, right? If it lasted 5 years, I was good with it. I was good with it. So you have to mop this on, right? While it's still wet from the silver, you mop this stuff on. So I did that, and now I put the thing back together. Again, this is the 44-inch before the coatings, and this is the 44-inch after the coatings. All right, so how am I doing now? Yep. Feeling pretty good. Feeling pretty good. So the mirror is now corroded. Okay. So it's 3 years later now, right? And the mirror is now down to 78%. And the NASA coating, I think, actually did the job. It actually did the job. The problem is there's any little pinhole through the silver or through the coating, the pinhole gets the thing and it starts opening up into a dot and then a mark, and it just kind of gets bigger over time. So I got blotches growing on the mirror. But I'm going to take it out again. Maybe I'm going to call Clausing again and see what I got to do to get him to do it. But maybe he's changed his mind, or I can sign some kind of legal disclaimer. But I'm going to take it out again here this year and recoat it again, one way or another. I'm going to get it recoated again. So after all this, all right, now that we've got something happening, what can it do? Okay, this is an 18.7 mag star. And it's 20-second exposures. And I will bet for the life of me, even though you guys are all pretty sharp and done a lot of astronomy, you can't tell what this light curve is coming from. Anybody want to take a guess? All right. This is a 14-minute binary. 14 minutes. 14 minutes. I didn't know such things existed. Arnie, what's the story on that? These things, there can't be many of them, right? He's thinking about it.
They don't last very long.
Okay, they don't last very long. That's the whole point, all right? Bruce and I are measuring this star, and we're trying to see the spin down rate. This is cool. To us, this is cool. It should be cool to everybody in this room. If we can measure the spin down rate, we will tell when this thing is going to go into gravity wave production, right? And we will be the first amateurs to contribute to the gravity wave research in that area, which I think is pretty damn cool. So yeah, we're watching this thing. Right now, it's ambiguous whether it is or it isn't. So it's going to probably take a couple years. So we're asked the question again, is it over? Because I said first light was in 2022, and I said this is a 26-year journey. Is it over? Not quite. So occasionally I would have oblong stars. Occasionally, right? Out of 100 images, maybe there would be 3 or 4 or 5 in the set that were oblong. So I didn't think much about it, right? Okay, probably got glitch in the thing, bump on the wheels or something. Had another problem with the electronics where the AC motors were losing their phase angle after a couple of days. It would take a couple of days. And I was on the phone with Dan Gray about it. He logged in, and we went back and forth on this thing trying to figure out what it was. And he couldn't figure out what it was. So I said, okay, I'll have to live with it. Every couple of days, just push a reset button, you reset the phase angle on a thing, and it runs fine. When the phase angle goes out, it decelerates horribly or accelerates horribly. So that was the problem. So this year, literally this year, 2026, I switched the drive motors for the dome from just 220 AC motors that go gung, 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 when I wanted to move it a couple degrees, to servo motors because my neighbors were going to hear this thumping all night and I didn't want to piss them off. So these servo motors accelerate and decelerate. They're beautiful. And they make that familiar high-pitched whine, right, where it's pulse width modulating the motors. And my stars went nuts. All my stars went nuts. And my phase angles didn't last 5 minutes. It was a noise problem caused by the thumping of the AC motors. So I had to replace all the wiring for the 220 motors in the dome with highly shielded cable. I've got aluminum foil wrapped around the driver. I've got everything crazy on trying to get rid of the noise. And I called Ash Dome about it because I called Ash Dome originally. I said, hey, I want to go to the servos. I go, you got a kit? And he goes, we can sell you the motors. He said, well, you should go buy this servo, this variable frequency drive for the stuff. This is what we're using. It's great. So I called him up and I said, there's a frequency problem with this thing. And they said, okay, we'll look into it. And that was months ago. Just last week, they sent me a thing saying, yeah, we had another problem with that. We found out there's this filter you can get. Here's the filter. You can go buy it for $200 on so-and-so, right? So they finally are coming alive to it. So I was at the front of the spear on that one. I must have some arrows in my back. So I'm calling it now officially finished in 2026. It's been doing science for a little while anyway, right? It's not like it's been sitting on doing nothing. But the only problem left now is as a memory leak, which has something to do with the Gemini focuser. Optech is looking into it, but that's not an issue. Certainly not something I can mess with anyway. So, to wrap it up, things that were not a problem. Mirror cooling was not a problem. I've not had any problems with a hot mirror. I have no idea why. It gets hot in my dome like everybody else has got a metal structure around their telescope. I get a huge focus shift through the night. You saw the trusses going up. They were silver, right? They're electrical conduit. I was originally intending to switch it out to carbon fiber. Carbon fiber is like $7,000 for a set of tubes like that, right? It's ridiculously expensive. So I left them on there. Let's see what happens. Focus shifts like 1/8 of an inch through the night. Ridiculous amount, right? You have to move the focuser thousands of counts through the night. Turns out, if you move it that far in the night, you can get an exact plane, because it's all steel, on where your thermal thing is, and you can adjust the focus automatically with the focuser according to the thermal equilibrium of the thing, and it's not a problem. I couldn't believe it. It's not a problem. I don't focus for a couple days sometimes, right? I don't focus for a couple days. So that was not a problem. You can ride it while it's tracking. You can get on this thing and do the merry-go-round thing, and nothing changes if you're monitoring the star, right? Nothing is star. I tell people to use the telescope as a handrail when they're coming up. Mark has been there. And, people come up and there's no railing up there because the telescope would hit it. So I tell them, grab onto the telescope. So the telescope is a pretty sturdy piece. It's a half wave, and I'm seeing limited. My general seeing is about 3 arc seconds, right? So I'm as good as I need to be. I don't know how good it'll ever be because I'll probably never get to a better seeing thing. So lessons learned. Coatings are important, guys. Way more than you think. I know people let their coatings go for 10, 12, 15 years, and they don't think about it. If you've got a really old telescope, I would go measure it with the camera thing and see where you're at. You've got all the tools already. Available time in my situation was the biggest drawback. It wasn't so much financial, because I did this pretty much on the cheap, and I did have help. Like I had a benefactor for the dome. Mark was very helpful on things. Big thing that you guys should understand is that a highly efficient small scope is very competitive. It's very competitive. You shouldn't think, like I thought, that if you get a big scope, man, you're going to be in a whole different world. You're not that far away. Signal and noise is about 1/3 in my telescope that it is in Bruce's when it's up to speed. So it's not that thing. So these are some of the lessons learned. The field can out-evolve you. Going to exoplanets now is pointless. Nobody cares. And you can't do it alone. You cannot do it alone. So I want to thank these people. All of them contributed greatly to this. Peter Cervallo, I want to tell you a little story about Peter before we wrap this up. I think many of you know Peter Cervallo, Canadian guy, makes mirrors and stuff like that. He built a space telescope optics and stuff. So I'm communicating with him about all this stuff. And while I was doing all this, he figured a 1 meter mirror in like 2 weeks. Peter, how the hell did you figure a 1 meter in 2 weeks? He goes, I ground it. Hey, what do you mean you ground it? He took the grinding, you use cerium oxide when you're polishing. It doesn't actually grind any quartz away. It melts the quartz like putting water on soap, and you kind of brush it away. He used grinding compound, silicon oxide or something like that, and he ground the figure in. I said, how'd you measure it? He goes, I just wet it down. So I could have ground this thing, wet it down, and see what I got close, and then started polishing. It wouldn't have taken me years to polish this thing had I known that. I was like, crazy. So, I'm going to leave you with something here to give you all hope. I'm going to give you all hope that you won't have to go through what I go through to get a 1 meter telescope. Right? We all want a 1 meter telescope. Most of us can't have it. But what if it was possible to get a 1 meter telescope on a Paramount that only weighed 150 pounds and was about the cost of an expensive Corvette? Wouldn't that be great? Now, I don't know, not all of you could afford it, but probably more than one of you might afford it, especially if this is the last hurrah. If I'm going to my grave, damn it, I'm going with a big telescope, right? Because that's what I'm going to do. I'm going to my grave with a big damn telescope. So, this is not ready for prime time yet, but there is a possibility that this may happen in the future. So, thank you very much. I'm willing to answer any questions. My opus grande, 26 years is finally get to make the talk. Yeah. Arnie. Oh, wait, it's coming. Hold on.
So I'm a bit curious. You said that your first light curve was a 14-minute binary. Did you ever identify what that was?
Yeah, I don't know what the number is on that thing, because these license, we look at a lot of license plates on all these stars. And I put more descriptive names. The subdirectory is 14-minute binary. In the Sky X, it's 14-minute binary. I don't know what the number is. We do know the number. It's probably published somewhere. There was a few of them that were very fast, like less than half-hour binaries. This was one of the more interesting ones. But where are you? I don't know where you're at. Raise your hand. Oh, okay. Yeah, that's your answer. Give it to Arnie.
Other questions?
Yeah, Arnie's got one up here.
Hello. Yeah. I think there's a couple dozen, actually, of the short period ones.
Are there? Okay.
But the thing I found was that the best thing to do to get high efficiency is to go to a good seeing site. So I had a lot of experience with 1 meter telescopes at USNO, and I was always outperformed by another 1 meter telescope that had sub-arc second seeing, and I had 2 arc second seeing. And so probably a 24-inch at a sub-arc second site will beat your 44, is my guess.
Well, that's advice to take, right? Because now you can get a telescope of your own down in Chile. I don't know what that altitude is. How many people here are using a telescope in Chile?
5,000.
Yeah, at least 3 of us are using Chilean telescopes. So yeah, that's some good advice. Listen to Arnie. Don't blow your money on a 1 meter. Get a good plane wave and spend the dough on a good site.
13,000 a year.
Okay, there you go. 13 grand. Just get rich.
How did you do your field derotation, or did you not?
It's derotated. It's a Gemini focus. It's a combination focuser rotator. You didn't see it. It's in there. But you don't see it's black.
What are your future plans for this scope?
Well, currently we're looking at these white dwarfs that have these dust clouds around them that appear abruptly. And maybe this will be my talk next year, but you brought it up. We look at this group of white dwarfs that have, the theory is that there's an asteroid in orbit around them. It's a fairly short orbit, 4 to 12 hours, in that kind of category. And suddenly these dust clouds erupt and create big dips on these things, and they hang longer than they should. And then they go away. And these white dwarfs can be inactive for years and then suddenly appear again. So we were monitoring this one star, J0328. I happen to know that license plate. And it normally showed 5 to 10% dips for the last few years that we've been looking at it. And this year, it showed a 40% dip, which is way out of the ordinary for this star. So we have some professional astronomers that we work with, so we called them up and we said, hey, 328's doing a 40%er here. And they go, wow, that's crazy. We're going to jump on this thing. They went to get time on James Webb, and it was a year to get time on James Webb, which you expect is typical. But they called the director, right? And the director gave him time in a week, and we got 13 hours on James Webb. And that went down a couple of months ago, and they're working on the paper now. So maybe I'll be able to talk about that next year. So that's the kind of thing we're doing. We are doing things, we found that the professional community wants to hit and run on papers. Papers is the currency. I'm sure Arnie will back me up on that. Papers is your currency in the professional world. And they're not going to waste their time just looking to see if something else is going to happen to a star. So that's where we come in, is we can monitor these things on a continuous basis. And if something comes up, well, we can notify them. We can all get on the paper together. It gets exciting. But the other thing that's happening, for instance, this white dwarf 1145, I've talked about it here before. Between me and Bruce now, we have almost a decade of data on this star. And we're seeing a periodicity of 125 days, which we think is an interloper that comes in and whacks these asteroids every 125 days. So one of the problems is that how do you go a couple of years without hitting an asteroid? And I'm working on that problem right now using AI to help me design the software to analyze that. So that may be another thing I talk about in the near future here. Did that answer your question?
Yes, thank you.
Mm-hmm.
Any more? Going once? Twice?
Time for alcohol?
Thank you very much.